Hi friends, this is Gaurav and you are watching Learn with Gaurav. So today's topic is DART space mission by NASA. DART, Double Asteroid Redirection Test, a remarkable planetary defense driven test by NASA. This is the planetary defense driven test first ever conducted by NASA. Move on to next slide. This is DART with large rollout solar array. You can see here two wings of rollout solar array or ROSA. This is the Draco and this special kind of telescope cum camera, and this is the advanced aerial propulsion system called Next C. So move on to next slide. This is the attribution for the previous picture. So move on to next slide. This is mission schedule. You can see here launch period has been mentioned. Launch period is mentioned here, November 24, 2021 to February 15, 2022. But actually in November 24, 2021 it has been launched, and of course through the vehicle as mentioned here, Falcon 9 rocket by SpaceX. So here the impact time, that is impact duration, probable impact time has been given here, the range September to October 2022. Actually it has been hoped or it has been predicted that the impact will take place within the two dates from September 26 to October 1, 2022. At that time, the velocity of that spacecraft will be 15,000 miles per hour when it will crash with the target asteroid called Dimorphos, having diameter 160 meters, and it has an orbital period of 11.92 hours while revoluting around another larger asteroid having 780 meters named as Didymos. Both have the separation 1180 meter separation between centers. So you can see here mission duration is mentioned as 10 months, and here you can see also the secondary asteroid named as Lycia Cube, Light Italian CubeSat for imaging of asteroids, ASI contribution. This will take the images after the impact, because after the impact already the DART spacecraft have been crossed. The mission is to deflect the Dimorphos or asteroid. So move on to next slide. This is the attribute for previous image. So these are the technologies associated with DART. First one is Draco, Didymos, Reconnaissance and Asteroid camera for optical navigation. Next, Smart Nav or small body maneuvering autonomous real-time navigation. Next, C, NASA's evolutionary xenon thruster commercial. ROSA, rollout solar array. RLSA, radial line slot array. Lycia Cube, Light Italian CubeSat for imaging of asteroids. Transformational solar array. CoreSat, Core Small Avionics Suite. Move on to next slide. So first let's come to Didymos, Reconnaissance and Asteroid camera for optical navigation. So it is of course a high resolution imager because we need clear picture for detailed analysis of the object that has been detected in the long range of telescope view field, right? So here it is derived from New Horizon Lowry telescope cum camera. Of course it has aperture 208 mm, field of view 0.29 degrees, narrow angle telescope, of course you can see here. So special technology used here is CMOS or complementary metal oxide semiconductor detector. It supports Smart Nav. It has a good coordination with Smart Nav. So designed for detection of objects and their relative locations and capturing clear images of the detected things so that the shapes, sizes and other visual characteristics can be analyzed properly in the seconds before the impact. So move on to next slide. Small body maneuvering autonomous real-time navigation or smart nav. It is a software-based autonomic movement and orientation control over the spacecraft. So the objective of this software system or algorithm set system is GNC, or if we expand it, it comes to guidance, navigation, control. To identify the proper small body, to identify the proper asteroid, which is the small body asteroid named Dimorphos, not the Didymos, that is the larger asteroid. So from separating the former one from latter one, guidance is needed, and this guidance is provided by the smart nav, and of course accordingly the navigation and control is carried out. So here is the very much high and pronounced coordination of smart nav with the hardware systems. Of course, very good coordination with Draco. In the right side, there is an algorithm or processing sequence. First, image is captured by the Draco of which the target object or any object coming on the way to the target. So next comes optical data conversion into digital data. Of course, the optical data, which is actually the image, that is converted into digital data. Now the digital data activates the algorithms or programs set for different conditions. So one condition will enable one program or one algorithm. So after the program is run, that is the high level language is run, then the command will be also in high level language, which has to be converted into low level language or machine language, which is nothing but the signals having digital signal or binary digit signal or 0 1 signals like that. So those have to be converted into analog signal. So after conversion into analog signal, the analog signals control the hardwares in their level. That means control the navigation system in hardware level. And this is why the orientation is maintained while traveling through the space. This is why in this way accidents may be avoided, like accidents with other asteroids coming on the way to the target may be avoided, right? It has been developed by Johns Hopkins Applied Physics Laboratory. So move on to next slide. This is NEXT-C or NASA's Evolutionary Xenon Thruster Commercial. It is of course an advanced ion propulsion system. DART is the first to use this, based on Dawn propulsion system. Actually, there was a space mission called Dawn and Deep Space 1, where a kind of ion propulsion system was used. So after improving that into a new version, NEXT-C has been developed. So developed with the help of NASA's Glenn Research Center, Johns Hopkins Applied Physics Laboratory and Aerojet Rocketdyne. As xenon satisfactorily fulfills the requirement of the propellant in the ion propulsion system, it is used here for effective results. NEXT-C technology has been tested for 51,000 hours, can you imagine, even without failure. It is equivalent to almost 6 years. A high power propulsion system operating 3 times more the power operated by NSTAR. Approx 3.5 kilowatt power is needed to operate this. The system the next C system saves time and operational cost due to lots of improvement. Move on to next slide. So this is the next C propulsion system. You can see here a minute grid-like structure. It is nothing but accelerator grid, which exerts the ion system. Which exerts the ion mixture with ion combination, whatever you say, a gaseous state or just converted state from plasma to the outer environment. Actually, this produces thrust, and xenon has high atomic mass. This is why in combination with a lot of xenon atom, the total mixture has a high mass. This is why a high propulsive power is applied here. High propulsive force is applied in the opposite direction in the opposite direction of its expelling direction. Direction of the expulsion. So move on to next slide. Attribution to the previous picture. Here is the given. So this is the fundamentals of the working of ion propulsion system. First, solar energy is collected by the onboard solar cells of spacecraft is converted into electrical energy. Solar energy collected by onboard solar cells of spacecraft is converted into electrical energy. Of course, with the help of the electronic system, electrical energy enables hollow discharge cathode. Electrical energy enables hollow discharge cathode to emit electrons through harmonic emission. After that, emitted electrons are attracted to the discharge chamber walls, having high positive voltage applied by the discharge power supply. The electrons, having entered the discharge chamber, bombard the already present heavy electrically neutral propellant atoms and ionize them, producing a mixture of plasma. Do you know what is plasma? Of course, plasma is the mixture of positive gaseous atoms and electrons which have been isolated from that particular atoms. Actually, there is extremely high temperature. This is why the electrons and the ionized atoms, that is the ions, cannot be fused, right? That is called plasma. So here in the high heat plasma is created. Actually, before, it is not the high heat first, it is actually the striking force of the electron into the neutral atoms. Here the atoms or propellant atoms is of xenon, of course. So after that, availability of electrons within the discharge chamber is increased by the magnetic field of discharge channel walls, and this increases the ionizing effect as well. Of course, you know, unlike neutral gases, plasma responds to magnetic and electric field, right? So after that, special configuration of the screen grids of high positive charge enables the plasma to stay at high potential, and this screen grid forces the heavy cations through apertures. Another grid having high negative charge, called accelerator grid, attracts the cations and makes their ways through the apertures, giving them high speeds up to 90,000 miles per hour. Can you imagine? 90,000 miles per hour. Extremely high speed, and of course more effective than normal gaseous propulsion system. As the grids are placed at rear end of the spacecraft, as I know, the heavy cations are expelled out of the spacecraft, eventually producing high thrust on the spacecraft. Now you know, the expelled thing is nothing but mixture of positive ions, and that is cations. So if they are not neutralized, they will be drawn back to the spacecraft due to highly negative charge of the accelerator grid. This is why equal amount of electrons are ejected by the neutralizer which is another hollow cathode, to electrically neutralize the ionized propellant, right? Move on to next slide. ROSA, or Rollout Solar Array, developed by Redware's Deployable Space Systems, Coleta, California. In spite of the demonstration of this in International Space Station in 2017, DART is the first to use this technique in any flight space mission. It is quite different from traditional solar panels. So let's compare between this. Traditional solar panels and rollout solar array. Traditional solar panels are heavy and bulky, whereas rollout solar array is light and compact. Traditional solar panels remained folded with the help of mechanical hinges before jettison. Rollout solar array remained rolled in with a compact, flexible central wing before jettison. Traditional solar panels, after jettison, unfolded and expanded, whereas rollout solar array, after jettison, rolled out and expanded. This rollout solar array is more effective in power supply, especially in the case of propulsion system. Installation of it in DART was completed on 13th August 2021 in Applied Physics Laboratory. It is approx 8.6 meter per wing in length, of course. 2 wings have been used here, in DART. Approx 240 square feet surface area of the arrays to deliver the required power to ion propulsion system. Move on to the next slide. Transformational solar array. This is actually a new version of ROSA, which has high efficiency solar cells and reflective concentrators. Thus, small portion of ROSA has been configured to this configuration made by John Hopkins Applied Physics Laboratory. Actually, potentially, it is much useful in future interplanetary mission, as NASA thinks. Move on to next slide. This is Transformational Solar Array in Applied Physics Laboratory. Actually, this is the final checkup in this laboratory. You can see here, and this is attribute for the previous image. So move on to next slide. Radial line slot array. It is high gain, low cost antenna. You can see here the round disc-like structure having T-shaped slots. So it is high gain, low cost antenna, high efficiency communication due to having unique capability of both sending and receiving data. So here the credit is given for this picture. So move on to next slide. Core small avionics suite. It is software and electronics based interface system among image processing, communication and propulsion system. Single board computer and interface module. Coordination among multiple systems of the spacecraft. So move on to next slide. What is the next slide? Actually, we have reached the end. So thanks for listening. This was a brief report on NASA's new mission, new planetary driven test mission. It is, of course, undoubtedly one of the most crucial steps that has to be taken to save our Earth from hazardous and dangerous much big asteroids, right? So if you have liked this video, please hit the like button and subscribe to this channel if you are new in this channel. So thanks for watching. Stay healthy, stay safe. Thank you.